G'day there, you're watching the Aussie BIM Guru, and today I'm covering a tutorial in Dynamo about how to automatically place GPOs in rooms. So quite an exciting tutorial. I have to give credit to Sean Fruin from Sigma AEC Solutions for the inspiration behind the script. Essentially he shared a video of this script on LinkedIn that I saw. Obviously there's not a script building video, so I thought I'd build my own version and share it with the community. So hopefully you enjoy. So thanks, Sean. So the workflow essentially that I've interpreted from this is to start at the door of a room. So you specify a room and specify a door, and then you specify an offset from the door to begin placing outlets in a counterclockwise or a clockwise direction, spaced equally around the room based on the number of outlets that you specify. So I'm going to show you how to do this in Dynamo. It's a really handy script, and I think it'll help a lot of people in schematic design phases for placing outlets based on count. We're not going to use any custom nodes today, which is great, so it's all out of the box. I'm going to be using version 2.0.3, but I think anything in the version 2 point somethings would work, and I think it's possible to build this in version 1 as well, but you might need to use some different list management techniques. So without further ado, let's get started and just jump straight into it. So I've just got a model here where I've set up a room with a door, and I've got outlet families I can place. So obviously if I was in a project, I would usually have to go and place these one by one, and if I wanted to place them at specific spacings, I'd need to measure this myself, and obviously it's quite clunky. My outlet family actually isn't wall hosted. I prefer to make these standard level hosted families because I find it easier to control them and to host them in nested families as well. So essentially this is the outlet family I'm using. It's really just a extrusion and a couple of nested buttons if you want to build one at home, and it has a symbol in plan which shows you that it's a GPO, and essentially that's all it is. And it's work plane based, and it's a shared family. So if you want to replicate this workflow, you'll probably need a family built in a similar way, so not the default Autodesk outlet. So what we're going to do is we're going to try and build the script so that it can handle a few different shapes of rooms. So I've made some more complicated room shapes here. I believe it won't work for rooms that have a torus in the middle, like a donut shape. So if the room was a bit more like this, it may not work. So just keep in mind that this is built for more generic shaped rooms with a single boundary. Okay, but let's just jump straight into Dynamo. So the first thing we're going to do is we're going to get a door and a room. So we're going to use the select model element tool for both of these. So we're going to get two select model elements. Notice I'm running in automatic mode. So this script is okay to run in auto mode when you're testing because we're going to be dealing with geometry, so it'll be helpful to see that dynamically update as we go. Okay, so let's just call this select door and select room because we're going to be building this for Dynamo Player as well. And we'll right click these and we'll make them both inputs. Okay. What I'm going to do is just jump into Revit temporarily, and I'm just going to get the door and also get the room. So we'll select our door and we'll select our room, and essentially this should be enough for the script to work with. Okay, so what we're going to do first is we're going to get the door's location. So we're going to use get location, and this will give us a point for the door. So this is where our door is located in space. What we're going to do then is also get the room finish boundary, so we can see the outside of our room. And we're just going to create a polycurve as well by joined curve. We'll just do a zoom fit. So now we can see our door and our room outline. But we're going to turn this into a polycurve by joined curves. So we're going to search for polycurve by joined curves, just to turn this into a single curve rather than a set of curves. And we'll just do a join tolerance of 0. Okay, so now our output we're dealing with is a polycurve, so we can work around this curve using the point parameters. So what we're going to do next is we're going to add the option to reverse the direction of the curve, because maybe we want to work clockwise or counterclockwise. So we're going to create a reverse node, and we're going to reverse the direction of the curve as well. And we're going to use an if node to let the user specify which way the curve should be going. I believe by default it goes in the counterclockwise direction, but we'll test later on. So what we'll do is we'll feed in a boolean. Actually, it goes in the clockwise direction, I think. And we're just going to call our input a true false of clockwise. So are we going clockwise? If we are, then we'll feed in our reversed curve. If we're not, we'll feed in our standard curve. And we can continue on with whichever output we get out of this. I'm not sure if there's a curve direction node that can show us. We might be able to. No, I don't believe we can. So I'll have to show you this later in the script. Okay, but what we're going to do now is we're going to find the closest point on this curve to the door's location. This is our starting point for our outlet placement that will offset to achieve our first outlet. So we're going to find the closest point between our curve and our door's location. Okay, so that should give us another point that's actually on the curve. So what we can do now is work with the parameters on the curve. So how far around the curve are we between 0 and 1? So we're going to get the parameter at that point. So at this point on this curve, what's our parameter? And we see that currently we're sitting at a parameter of 0.31. So we're about 30% around the curve from its start point. So what we need to do now is remap this so that we can keep working around the curve with an offset as well, and treat this as our start point, because obviously this isn't the start point of our polycurve. So what we're going to do now is just create a number slider. And this is going to be our offset from the door. So we're going to call this offset from door. So obviously the door's location is the center of the door, which isn't what we want. So we'll do a number between 0 and let's go up to 1500 with a step of 50. So this will let us specify, say, an offset of, say, 750, for example, in this case. We also need the length of the curve. So we're going to use curve length to find out how far along the curve this will place itself as a parameter. So now we know the length of our curve, our offset, and also the parameter at the point that we've specified. So we're going to create a code block formula at this point. So we're going to say that the first parameter is equal to an offset over a length. So we're processing our parameter by the offset over the length of the curve to find out how much of the parameter is associated to that offset. Because we need this to be a number between 0 and 1 in order to work with point parameters. We're going to say parameter 2 is equal to the point at parameter that we've got from previously extrapolating our door's location. And we're going to add on the parameter of our offset. So we'll get 3 parameters. The first one is going to be our offset, our length, and our point at parameter. So essentially this gives us a method by which to find out where the offset parameter point is going to occur. What we're also going to do is set up a sequence to determine the spacing of all the other outlets around the room from this point. So we need another code block to do this. So we're going to say that sequence 1 is equal to 0, ... 1, ... and then hashtag x plus 1. So essentially we're establishing a sequence with the number of items within the sequence between 0 and 1 to be a number we specify plus 1. We're then going to say that sequence 2 is equal to, and we're going to call on a core function here. So we're going to do ds_core, we're going to call on a list function, and we're going to do remove item at index. And we're just going to remove the first item in the sequence. Sorry, the last item in the sequence, sorry, because the last item is essentially the same as the first item. By the time we get around our curve from the start to the finish, we'll be at the same point. So we don't want to place 2 outlets at this point, we just want to place 1. Okay, so the only variable we need here is x, and x is going to be our number of outlets we want to place. So we're going to create a number slider. I'll just take this one. I'll probably need to make this an input as well. Okay, so this one will be number of outlets. And we'll just make this a number between, let's say, 2 and 15 with a step of 1. By default, let's just put it around 6. So this will give us a sequence, and then that same sequence without the last item as our output here. Now what we need to do is add these together, because essentially what we have, I'll just get a watch node. What we have is a list of points at parameter. However, we also aren't starting at 0, so this sequence isn't currently correct. what we really need to do is offset by this number. So we're going to do add. We're going to do plus and to this number. We're going to add this number onto every single point in our sequence, and we're going to do our longest lacing. So we should end up with the points at parameter offset. However, some of these points are past 1, so they won't work correctly for a parameter at point or a point at parameter. So we need to make these go back down to below 1. So we're going to make a little code block again. So we're going to check if this number is greater than or equal to 1, because we want to process these. If it is, we're going to make that number take 1. If not, we'll just let it be that number. So the only input we need here is x. And what we're going to do is feed these into an if node. So we're going to test for this condition, and if it is true, if it's more, we'll make the result take 1, otherwise it will be the opposite. So what we'll end up with instead is a sequence with these last two numbers corrected down by 1. So that's how we can process these figures. So essentially what we have now is the parameters at point that we want to place our outlets at. So what we can do now is do a point at parameter. So that's pretty much the fundamental part of the script covered. So these are our parameters, and our curve is going to be our polycurve from back here. And what we should get now is a whole set of points. They're a bit hard to see at the moment because our curve is in the way. But if I can hide these, and also hide this. So point at parameter. Needs to be our longest lacing. And there you go. Now you can see all our points occurring around our polycurve. So I might just go back and turn one of my polycurves back on. But there you go. You can see essentially now we have these spaced. And obviously if I go back and I update my offset from door, you see that all my outlets move around the room to suit. So this is why automatic mode is important. Likewise, I can add more outlets to my room, and it figures out, based on the point at parameter formula, where these points are going to be to equally distribute themselves around the room. So pretty cool, right? So that's the fundamental part of the script done. What we're going to do now is also find out the normal to the curve at those parameters as well. So when we're at this point, we want to find out which way our normal is, because this is the orientation of our outlet, essentially. So we're going to take those parameters, and also we'll take our curve again, and we'll do a longest lacing so that we get all the normals. So for each of these points, we now have their normal as well. From here, we need to process these a little bit more. So the first thing we'll do is we'll figure out the orientation of the vector. So we're going to basically use another if formula, because I'll show you in a second sort of the problem with what we get. So actually I'll show you now. So we're going to do line by start point direction length. So our start point is the outlet's position. Let's just say the direction is the vector. And for the length, let's just make this a meter. You'll see that my vectors are all facing the wrong way. This isn't obviously ideal, everything is incorrect. So let's just move this around a little bit more. So you'll see that we actually want these all to face the other way. So what I'm going to do is feed in another if node. So I'm going to take the reverse of my vectors as well. And depending on whether it's clockwise or anti-clockwise, we'll want to flip these. So we need to get an if node again. And we're going to go back and extrapolate our clockwise parameter. So we're going to say if clockwise. And if clockwise is true, in this case, you're going to want the, sorry, we need to get the reverse vector, not the reverse curve. So we'll get reverse vector. And if it is true, we'll get the reverse. If it's not, we'll just get the vector as it is. And this is the orientation you'll need for a front-facing family in order to be placed in the right direction. From there, we need to process this vector to find out the rotation that the family is going to need to be rotated by in order to line up to this vector. Because all families will come in facing to Dynamo's north, essentially. So I'm going to create another code block. I've been using a few code blocks intentionally in this tutorial just to show you how code blocks can be used. So we're going to call on the y-axis vector. And then you'll need to put a bracket after it. I'm then also going to call on, I think I need to use a capital A there. Yeah, there we go. I'm going to just make a list of my vectors called vectors1, and I'm just going to make vector and then call on the z-axis. Okay, so I'm going to feed in my if result as vectors1, and I'm going to find out the angle about axis. Okay, so I'm going to be looking at these vectors versus the y-axis about the z-axis. So that's essentially what I've built that code block to do. This will give me an angle that these need to be rotated by. You can see we're getting some strange little anomalies here, these numbers that are almost 0. So I'm just going to apply a round function to this. And I'm just going to round to probably the nearest, let's say 3 digits. We want decimals to still be allowed. We just want to get rid of those really small anomaly numbers. And there you go. Now we can see these are the rotations that our outlets will need to be rotated by in order to position themselves inward facing to the room. I might just change this so that we can see the orientation of the outlets. In this case, my outlet's been built back to front, so I'm basically letting my vectors be this way around. If you also built the other way around, all you'd have to do is switch around these vectors to inward face to the room. So just test on your side with your family which way your orientation actually needs to be. I'm just going to freeze this for now so we don't have to worry about it. Okay, so I've got my angle to rotate my family by. I've got the position to place my family at. So I'm pretty much almost there. So what I need to do now is call on a family instance by point and level. So we're going to place a family at a specific point at a specific level. So in this case, I'm going to get a level, and I'm going to just make it a, for now I'll just place it at the level that I'm working at, which is called datum, but make this an input and just call this host level so the user can specify which level they want to place their outlets at. In this case, let's just specify longest lacing as well, because we're going to feed in one level for multiple points for one family type. So we're going to feed in our points, and I believe I might need to freeze this or go to manual mode. I think I might just go to manual mode because I don't want to run this just yet. I'll run it in a second. So we're going to get family types as a drop-down so that we can pick the family we want to place. In my case, I'm just going to go to my electrical fixture, which is somewhere down here. See, I've got a lot of families in this template. So I'm just going to pick my single power outlet, make that my family type, and I'll make this an input as well. Okay, and let's just call this family to place. Cool. So there's only two things left to do here. One of them is that I like to set up a formula that lets you specify the mounting height of your outlet. So the way that my outlet is built is it has a parameter in it which sets its mounting height. So if I just go up to component, I might need my properties browser back. And if I place this here, you'll see there's actually a parameter called mounting height. And I can actually change this to change the height that the outlet is placed at. So if I just zoom in here and go 900, you'll see that my family changes height. So I want the user to have the ability to specify what they want that height to be. So I'm just going to get a set parameter by name node. And for each of these families with the longest lacing, I'm going to just set their mounting height. I'm going to do this by specifying my parameter name to populate. You could obviously use offset as well if you don't have a shared parameter set up to do this. And then I'm just going to get my specific parameter in this case. So it's a mounting height parameter. And then the value. In this case, you could do a number or a slider. It's up to you. I'll just do a slider because I find users find sliders easier to work with. And let's just let them do a number between 300 and 3 meters with an increment of 50. So this can be a good way to sort of force your users to use a fairly rational placement height. Let's just make it 900 by default. And we'll just call this mounting height. And then last of all, we'll use family instance set rotation. And we're going to take these family instances and we're going to set their rotation to this number up here that we've calculated. So essentially once the families are created, they'll be rotated and also have their mounting height set as well. So let's just run a quick test outside before we use Dynamo Player. So So I'll just minimize this just so it's a little bit out of the way. And I'll zoom out and let's just try running this and seeing what happens. Cool, there you go. So you see all our outlets got placed at the right rotation and also at the mounting height that I specified as well. So really powerful. But let's run this through Dynamo Player now, just so we can test with some other rooms. And I'll show you sort of how it looks to run it through Dynamo Player, because obviously you'll probably do lots of rooms at once. Obviously you could change the script to handle multiple rooms at the same time, but I think doing room by room is safer, because then at least people get to think and review what they've done. You can see here with this specific orientation, we went counterclockwise. So we might want to go clockwise in this room, for example. This one here will go clockwise. So I'm just going to navigate to my folder in Dynamo Player, and let's just expand the inputs for our script before we run it. I think I've set all the inputs I need. Sometimes I forget one or two and have to go back into Dynamo Player and set them as inputs and then reopen Dynamo Player, but fingers crossed I've got them all this time around. Cool. Okay, so I think we've got all our inputs. So we'll select our door, we'll select our room. Let's just say we want a 900mm offset from our door, and let's say we want 12 outlets hosted at datum level. This is our outlet type at 900. It looks like I've forgotten my clockwise, anti-clockwise control, so I'm just going to go and set that really quickly. You can actually go straight to the script with this little edit in Dynamo button, which saves a little bit of time. It means you don't have to close this, reopen Dynamo, etc. It can take a little while to open because it is accessing Dynamo again. But once you're in, you can just change your settings, save, close, and refresh. So essentially, I'm just going to go into Dynamo, find that clockwise control. You might forget at least one. Set it as input. And you'll notice now it says file contents have changed. So we need to refresh or reload the script. It will refresh all of the inputs as well, so you will need to set your inputs again, I think. But it's basically reloading the whole Dynamo script with the new changes that you've made. Anytime now. Cool. So let's just set our door, our room, and let's just say we do want to go clockwise with an offset of 900, 12 outlets, and mounted at 900. And let's play. And there you go, it's placed our outlets. So how quick was that? Cool, right? And you can just go in and obviously change these into other types of outlets if you know you need a light switch at the entrance. Just toggle it over to your light switch family and you're good to go. Likewise, it can handle sort of more wacky room shapes because it's really just processing the finish boundary. So it doesn't matter what shape it is. And you're just going around the boundary in a clockwise or an anti-clockwise order. Let's go anti-clockwise. It's offset by 1100, and let's just do 7 outlets, and we'll just mount them at 1400. Play, and there you go. They're placed. So how quick is that? Super easy, super intuitive. You'll see that those ones we placed a little bit higher, and there you go. You can see that mounting height parameter has been populated by Dynamo. So really cool and really effective, I think, and should help some of my engineering followers out as well, hopefully, especially my electrical engineer followers. So great. So thanks for watching today. If you have any comments or feedback, feel free to leave it down below. Hopefully you find this workflow useful and it makes you think about other ways you could take advantage of your room boundaries and dividing them. Thanks again to Sean for the idea. And if you're not already feeling and subscribing, feel free to do so. I make videos 2 to 3 times a week, usually 2, but sometimes 3. And feel free to come along for future videos. Hopefully I'll see you in the next one. Thanks. Take care.